All right, this week we're looking at a titration question, and when it comes to these acid-base titrations, particularly titrating a weak acid with a strong base, or, if you had a weak base with a strong acid, there are a few things that you want to keep in mind, because if you can identify every point on the titration as a solution that we've already studied quite a bit already, it will make all these problems much more approachable. And so while these titration problems can be challenging, it does have a great tie-in of stoichiometry with chemical reactions, with tying in calculating pH for solutions that you already know how to do pretty well. So for this reason, it's really good to start with a graph of pH versus volume. So again, we're starting with a known sample of hydrofluoric acid, and we're adding 1 molar strong base. And here's what things are going to look like. If we read the blue graph from left to right, we initially start off, this is along the solid line, we start off at an initial point where we haven't added any strong base yet, right? And it's only going to be hydrofluoric acid. Then we get through this buffering region where we contain the half equivalence point. We then get to the equivalence point where we've added a stoichiometric equivalent amount of strong base to the acid. So that'll be a 1-to-1 ratio, as we'll see moving forward. And then eventually, if we keep adding strong base, eventually the solution would become a pH equivalent to the strong base that we're adding in the first place, as that goes to infinity. The pH of this solution should be above 7 at the equivalence point because we're mixing a strong base with a weak acid, and therefore that base is going to drive the pH up slightly higher compared to that weak acid. Or we can also think of it as when we're at the equivalence point, all that's going to be there is the conjugate base of this weak acid, so therefore a basic solution. Okay, if you weren't able to draw a graph with as much detail as this, that's totally fine, but do be aware that these are the points that should be the most interesting on the graph and are ones that will define what solution we're dealing with along each part of the curve. And so knowing the solution is of course very critical because we have different techniques for calculating different pHs for different solutions. And when we look at the initial solution, we haven't added any strong base yet, 0 strong base addition, and all we have is a hydrofluoric acid solution, which is a weak acid. And this we've done many times before. For a weak acid, we have the following reaction: partial dissociation of the proton from the HF, and we can set up our ice table. This is equilibrium, of course, so if we have an initial amount of HF, it's going to have a change to equilibrium. Our ice table is set up as so. We get our equilibrium row, and we solve this in accordance with a Ka that we already have. We can use our 5% rule, or at least try, and we get the following mathematical form, for which X is going to be the concentration of free proton. This is 0.0179 molar, which will actually pass our 5% rule, and we get a pH of 1.75. And again, this is the pH of nothing more than a 0.5 molar solution of hydrofluoric acid, which we've been able to calculate for some time now. For part B, we want to calculate the number of moles of NaOH that's required to neutralize the HF, and this is really describing the equivalence point, right? We have the following reaction, right? The strong base is being added. It's going to pair and neutralize 1-to-1 with this weak acid and leave us with neutral water and the fluoride ion. This is the equivalence point. We want to use stoichiometry. We will be left with some stuff afterwards. If we, for instance, wanted to get the pH, we would have to consider the fluoride ion by itself. But here, all we're looking at is the moles of NaOH required, the moles of the hydroxide, and it's just plain stoichiometry. The reactants have to be stoichiometrically equivalent. That's what defines this equivalence point. That's why it's named the equivalence point. And we just use stoichiometry, start with our volume of our HF, use the molarity of the HF, use the mole ratio, and what we need is 0.05 moles of hydroxide. That will neutralize the 0.05 moles of the 0.05 moles of hydrofluoric acid in our initial solution. Now that we've calculated the moles of sodium hydroxide that are needed, we want to calculate the volume that's required. This is going to be the x-axis value that gets us to the equivalence point, the volume of this strong base addition that we need. And remember that we already know how many moles are required. That's the first step, and what we're looking for is how much volume of a 1 molar solution is this going to be. This is again just conversions with molarities. So we use the molarity, it's 1 molar, and we find out that it's going to take 0.5 liters of hydroxide solution, NaOH solution, or 50 mils. Now, the last question is saying, well, the point at which 50% of the equivalence volume, so in this case it would be 25 milliliters of hydroxide has been added, we call this the half equivalence point, and we want to calculate the pH at this half equivalence point. And note that this is a labeled point on the initial titration curve and is really an important one to know. In this region, between the initial solution and the equivalence point, it's basically a buffer because we are converting the weak acid to its conjugate base, and therefore we have weak acid and conjugate base all throughout this buffering region. From this, we can use the buffer equation. So this is Henderson-Hasselbalch, pH equals pKa plus the log of the base over the acid. We can just use moles for this. We don't have to use molarity, but molarity is fine. Remember that they're in the same solution volume, so it really does represent the same thing, this ratio. Remember here that if we're at 50% equivalence, this is when we've converted half of the HA into A-, and therefore we have half of the HA remaining and half of the A- has been formed. So they're equivalent here, which is a little bit confusing, right? The two concentrations will be equal when we're at the half equivalence point. The equivalence point is when we've converted 100%. So just keep those two things in mind. But when we are at 50% equivalence, this is when the buffer equation is going to simplify just to pH equals pKa, and that is all you need here. Get the pKa of the HF. We have its Ka, so take the negative log to get the pKa. That'll be the pH, and we see that this pH is slightly higher than the initial pH that we started with.